Welcome back everyone to a new video. Today I'm actually going to step back a little bit from all of these complicated linear transformations, these vector transformations or functions, because I thought that we took a little bit of, it was a little bit of a difficult jump over to transformations. I think, yeah, it was a little too far of a jump. I just was kind of excited to talk to you about it. But today I'm going to just take a step back, like I said. And we're going to look at some examples of vectors, okay? So just another visual intuition of graphing the addition and subtraction of vectors. So let's just take a look at some examples. So let me just get something clear here. Again, we're gonna look at vectors that are all members of the reals, or R2. And again, this just means that these vectors can be plotted anywhere in this plane, all the way like this. However, if these vectors were in R, or a member of R1, then they could only be plotted by one of these, they can only be plotted by one of these two axes. But today we are going to look at vectors in R2, or plane. Okay, so we're going to actually also look at some examples of scaling, or multiplying vectors by scalars again. Sorry about my voice, I kind of just woke up and I haven't talked this entire morning. Just been doing some nerdy things, just watching math videos. Anyway, so why don't we take a look at an example of a vector. So we have a vector A. Let's say that's equal to, again, column vector, row 2, I'll just, so you can get a refresher on that. So row 2, column 1 vector, of course, just a column vector. Let's say it is 0.3 on the x-axis and -2 on the y. How about let's have another vector B. These are vectors. I think I'm just going to describe them as position vectors today. And then this could be -1 and 4. Okay, so let's say we want to add A and B. So, well, normally what you would do is, what would happen is, you would essentially just combine the vectors like this. So a 3 sub, or 3 comma -2, and then you add these terms here like this, so they're aligned, and then 4, and then you would get this, let's say this is C, this new vector, which is the addition of A and B. This is just another column vector. It's 2, 2. Interesting. Okay, so that's what this is. But now I want to show you a little bit of a different approach of the addition of vectors when graphing them. So first of all, I want to make it clear, and this is kind of cool to me, that vectors can be expressed in any form, so infinitely on this graph. They don't necessarily, because some people, all they do is just graph them in what is called standard position, which is just essentially their coordinate. So it's essentially with their coordinate with respect to the origin. But in theory, you can just take any arbitrary point, like for example, 3, 2, 3, 2. So this can be coordinate 3, 2, and essentially we can describe vector A in this case as, so vector A, we established this vector A, 3, -2. So all we have to do is just go to the right 3. So I wish I had an established graph. So 1, 2, 3, right? To the right 3, and then down 2. So 1, 2. So this can be, this is a completely fine description of vector A. And, you know, why don't we just describe it here as well? Why don't we just have point -1 and then -1, right? So we can have this point, and we can describe vector A as, you know, again. So all it is, I'm just going to show you. So we can have any arbitrary point x1, and then x2, and then vector A, for example, or any vector A can be described as, or vector A in this case, just to keep things simple, can be described as x1 plus 3, and then x2 minus 2, right? So that's how you can describe this. So essentially it's just -1, so this is coordinate -1, -1. So x1 is -1, so plus 3, that's 2, right? So you go over to 2. So you go over 3, so it's just goes over here. And then -2, so that's -3. I can go there. And then, as you can see, this is essentially the same thing. It's just my inconsistent graphing, because I'm actually writing this down rather than computing it on a computer. But these are equivalent, right? But again, standard position. Why don't we write this coordinate in standard position? So these are all perfectly fine ways of defining vector A. So this is all vector A, right? We should probably have another piece of paper and graph it better. So let's write vector A in standard position. So all it is just the coordinates of vector A. So it's just 3 to the right, right? This is our coordinate, so it's just x is equal to 3, y is equal to 2, -2, 2 down, and there we go. That is another way of describing vector A. So that's vector A. Now let's write vector B in another, using another arbitrary set of points. And just to give you an intuition why this works from here is because these coordinates are 0, 0, right? So, this is another vector. This is just these. By the way, if vectors are collinear and you scale them, they can all be expressed by one line. But I'll get to that in a bit. But anyway, this works because, you know, let's say because it's all 0, so you can express A as 0 plus 3 and 0 minus 2, and you get these coordinates. So it's the same thing. So you don't really have to express it that way because it's just intuitive to do it this way without doing that. Anyway, so let's try vector B now. So let's pick a set of points. So this could be 4 and then 2. Yeah, okay, so we'll have 2, 4, points 2, 4, and then we want to express vector B. Okay, and that would be 4 to the right, right? Because 2 plus 4, so 4 to the right. So that we go to 6. That's 1, 2, 3, 4, 5, 6. So it's just 4 to the right. 3, 4. Okay, and then down 1. And that is vector B. Oh wait, my bad. I switched up the y and the x-axis, or the y and the x values, because look, I put -1 as our y, and that's supposed to be x, so that's wrong. I'll rewrite this. My bad. So 1, 2, 3, 4, same coordinates. So here, that's our arbitrary point. This has nothing to do with our vectors. So 2, 4. And then we want to express vector B. So that would be this point -1. So that'd be 1 to the right or to the left. So here, and then plus 4, so it would be 1, 2, 3, 4, 5, 6, 7, 8. So plus 4 would be like this, and this would be our vector. This would be our vector b, right? And then we can write this from standard position to show you that this is equivalent. So the coordinates are -1, so -1, -1, 4, 1, 2, 3, 4, right? Oh, I wrote that terribly, but just assume that it's like this. So you can tell that they are equivalent. So this is vector b as well, right? So now let's try adding both a and b, okay? So let's graph just to see everything from a nice perspective. Let's graph a, right? Because we start with a. Let's graph a in standard position, because I think that can make things less confusing. So a is 3 to the right, and then 2 down. So this is a, that's vector a, okay? And now, vector b, let's graph vector b, also in standard position. Actually, no, let's graph our new vector c that we got here, so 2, 2. Right, that's our new vector c, so the addition of a and b, so the sum of a and b, sorry. And theoretically, you can think of this as the head of vector a plus the feet, let's say the feet of vector b will get to vector c, right? Because how much, it's essentially saying how much does it take, what transformation does it have to undergo, right, to get to vector c. So let's graph vector b. So that would be b. That would be 1 to the right, to the left, sorry, right, -1, and then 4 up. So 1, 2, 3, 4. There we go. See, we formed some interesting triangle here. I'm not sure if that's a right angle, but that's pretty cool, isn't it? And this is vector b. So this just shows that vector, this proves that vector, so this is another approach of approaching things. That vector a plus vector b is equal to vector c, right? So why don't we now switch to arbitrary point just to hit the point home. I've really extended this video, that's cool. Just to make up for some of the days that I missed. Okay, so just need to memorize the points here. So why don't we start from, let's see, why don't we start from points? Oh, we'll see, it doesn't really matter. So 1, 2, 3, 4, 5. Yeah, why don't we start from 5 and then 2, 3. Okay, let's start from this arbitrary point. 5, 3. Okay, so now let's graph vector a. So vector a is 3 to the right, and 2 down. That's 1, 2, 3. It's over here, and 2 down. It's over here. So this is vector a. Vector a. And now theoretically, if we put vector b at the tip of vector a, so the toes of vector b at the head of vector a, then we will get our solution to a plus b. So this is an interesting way to find the sum of vectors a and b, or anyway, column matrices of column matrices. So let's graph vector b. So let's just 1 to the left, 4 up. So 1 here and 4 up. So it's 1, 2, 3, 4. So it's just here. So this should be our solution. And when we, if we graph vector C, it will look something like this. So this is vector C, or yeah, vector C. And this is vector B. Isn't that pretty neat? In my opinion, that is. So let's just make sure. So theoretically, vector C should go to the right 2 and up 2. And yes, it does, because you can see that, well, at least for the x-axis, so we can see that it goes 1, 2, and then up 2. I kind of graphed that weirdly, didn't I? But anyway, you can tell that's aligned with this, and then up 2, right? And that is our vector C. And again, from standard position, this would be vector C, and that seems to be equivalent, right? So now let's quickly, I might have to split this video up a little bit. So I'll talk to you guys in the next video. Hopefully I'll upload it later today. Hope you guys enjoyed, and see you in the next video. Goodbye.